Analysis of a roller coaster without a loop. A roller coaster with a mass of 1,000 kilograms begins from rest at position A and travels towards position D. You're to calculate the GPE, gravitational potential energy, KE, kinetic energy, ET, total energy, and V, velocity, for each position. So the roller coaster begins at the top of the ramp, and since it's beginning from rest, all the energy, the total energy, is due to the GPE. So I'm just going to make a note of that. So right up here, we have ET, total energy, due to GPEA. Now, another note I want to make right here is this position C, the feature of this roller coaster. That's called a camel hump. Because it looks like a camel hump. Okay, so another very important note that applies to the entire problem and every single roller coaster. Let me write it right here. In all cases, or in all positions, in all cases, positions, the total energy, ET, is going to be equal to the GPE plus KE. So let's put N here, represents any position. So this is the concept of conservation of energy. Conservation of energy law. Okay, so let's start solving this problem. We have 4 sets of calculations that we have to do. So let's begin with position A. And what do we know about position A? Well, we know that the velocity at A is equal to 0 meters per second. So we know that there is no kinetic energy because there's no motion, so the kinetic energy at A is equal to 0. So we have 2 of the 4 pieces of information that the question is asking. We have the velocity, we have the kinetic energy. So now I'm going to move on to calculating the GPE. So GPE at A will be equal to mass times G times the height of A. So the GPE is equal to 1,000 times 9.81 meters per second squared. And position A, we're at a height of 10 meters above the ground. So GPE works out to 98,100 joules. So that's how much energy we have. And we stated earlier that ET is equal to GPE plus KE. I guess this would be at position A. So ET is equal to 98,100 plus 0. So ET is equal to 98,100 joules. And again, this is for all positions. Okay, good. So that takes care of one calculation, or one set of calculations for position A. So let's move on to position B. So let's do that here. I'm going to be creative in fitting this all in one sheet. Okay, so we can't determine the kinetic energy at position B because I don't know what the, all I know is, I know the ET, but I don't know the velocity. Okay, and since I don't know velocity, I can't figure out KE. So what I'm going to do is figure out the GPE. So GPE at position B is equal to mgh at position B. So that's going to be equal to 1,000 times 9.81 times 4 meters, if you look at the diagram. And that means that my GPE at B is going to be equal to 39,240 joules. Now I can figure out my KE by looking at the total energy. So the total energy ET is equal to KE, and this would be at position B, plus GPE at position B. That's the total energy. And since I know the GPE and the ET, I can calculate the KE. So this is 98,100 is equal to KEB plus 39,240. So that means the KE is going to be equal to 58,860 joules. As you do this problem with me, and I'm saying you're doing this with me, check my calculations. So you know I'm doing it right, and then you can verify if you're using your calculator right. So KE is equal to 1/2 mv squared, and I can use that to figure out the velocity. So 58,860 is 1/2 times 1,000 v squared, and v is equal to 10.8 meters per second. By the way, that's approximately 24 miles per hour. Okay? Converting it to miles per hour is not a requirement, but just so you get a feeling for what this means. And that's for dropping a distance of 6 meters. We started off at 10 and we came down to 4 meters above the ground. So we fell 6 meters, and when you fall 6 meters, your speed is going to end up being 10.8. No matter how you got there, if it's a slow drop or a fast drop, that's the speed that you're going to have. Okay, so let's fit C in this area right here. And again, I don't know what the velocity is at C, so I'm going to have to first calculate the GPE at C, mgh. So I'm going to do exactly the same kind of calculation as I did for B. Nothing changes in the order of the calculations. So we're still 1,000 kilograms. G is still 9.8, but now I have a new height, and the height of position C looks like it's 7. So GPE, I should have said C right here. So C at position 7, that works out to 68,670 joules. Now my kinetic energy, well, again, I do the same calculation. KEC plus GPEC, so that's 98,100 is equal to KE at C plus 68,670 KE C is going to be equal to 29,430 joules. So when I climb up to the camel hump, I'm closer to the top of the original position, in other words, position A, or altitude A. And therefore, I don't have as much kinetic energy because more of the energy is gravitational potential energy. GPE plus KE is equal to the total energy. Total energy never changes. So if my kinetic energy is small, I expect that my velocity will be smaller also. So let's calculate that. So that'll be 29,430, and this is 1,000 times v squared, and that works out to 7.67 meters per second. Okay, so my speed has gone down. 7.67 meters per second is approximately 17 miles per hour. Okay, so that's the calculation for C. And I guess for D, let's squeeze it in down here. Now for D, because H is equal to 0, I know that GPE at position D is going to be equal to 0. So that was easy. And that means that the energy is going to be equal to KED plus GPED. So ET, oops, let's get rid of that. Try that again. That would be 98,100 is equal to KED plus 0, which means that KE at position D is going to be equal to 98,100 joules. What that means is that in this roller coaster ride, when you go from A to D, all the energy you have in position A in the form of GPE is converted into KE at the bottom of the ride. So there's a consequence to that, because if we calculate if we use the kinetic energy to calculate the velocity, you will see that the velocity is going to be quite high because all the energy was converted into kinetic energy. So that's where you're going to achieve your maximum speed at the bottom of the ride. So 1/2 times 1,000, v squared. So finally, v at position D is going to be 14 meters per second, and that is roughly 31 miles per hour. Well, thank you.